So there are two more operations that can be applied on signals. The first one is convolution and the second one is correlation. So in this video, let's talk about convolution first. In convolution, if you have an LTI system and you know the impulse response of it, then by using convolution, you can find the output of that LTI system for the given input. Again, if you have an impulse response of an LTI system, then by using convolution, you can find the output of that LTI system for the given input signal. Now, what is impulse response? Impulse response is the output of signal at a brief or a short input signal, which is called impulse. So let's come to MATLAB. First of all, here we have discrete input, which is equals to x 1 2 2 1 2, any random samples I'm taking. Now the range of signal x, which is nx, and it exists from -2 to +2 on x-axis. Let's take an impulse response, which is for say h equals 2 2 -1 1 2 2 and 1, with the range from -3 to +3. So generally we put the range of graph according to the number of samples. Like we have 7 samples in the impulse response h, so we have taken the value of range from -3 to +3, and which makes the total of 7 places. Now we have our input signal and the impulse response of a system. Now by using convolution, we can easily find the output of it. Let's set the limits for our output graph now. First, specify the lower bound and convolved signal, and for that declare a variable called nmin, which is equals to minimum value of nx, min nx, plus minimum value of nh. Now for the upper bound of convolved signal, take a variable nmax and add the maximum range of nx with that of nh, like this. Here we want to plot 3 graphs for input signal, impulse response, and the convolved signal. So type subplot 3 1 1 for 3 rows and 1 columns, obviously. Plot the input function using stem like this, and to get a clear graph, fill this with any color. Here I am taking magenta, and add the title for this as x of n. Now do the same thing to plot impulse response. Subplot, then plot the impulse response using stem. And let's fill this graph with red color now. Now define the axis for your graph. I'm taking from -4.5 to +4.5 on x-axis, and -2 to +3 on y-axis. Add the title as h of n, So up till now we have plotted our input signal, which is X, and the impulse response, which is H. Now let's convolve these two signals to get the output of the system on the given input. Take a variable, I'm taking Y equals to conv and X comma H. And by using this command, we can convolve both signals. This command is for convolution. Now specify the range of our output as from nmin to nmax, which we have already defined before. Again, to plot this output, use subplot, then stem n comma y with filled command. Give the title of convolution of two signals here. Mention convolution of h of n and x of n on y-axis and index of n on x-axis. And run this code now. You can see that we have an input signal there, impulse signal, and then finally the convolution of these two signals, or you can say the output of the system. So the last operation on signals that we are going to see in this course is correlation. Correlation is a mathematical function, and it is the measure of the similarities between two signals as a function to time shift between them. Correlation is maximum when two signals are similar in shape and are in phase. So we divide correlation into two types. Number one, autocorrelation, and number two, cross correlation. Let's talk about cross correlation first. In cross correlation, we measure the degree of similarities of two different signals, or we can say that in cross correlation, we compare two different signals and measure the degree of similarities between two of them. While in autocorrelation, we compare a signal with its shifted version. Let's take an example for cross correlation first on MATLAB. And to have the better understanding, we'll take an example of discrete time signal. So take any two random signals. Let's say I'm taking X and Y. Now assign the values to them. Now plot X and Y one by one. Here we want three graphs. Number one is for signal 1, and the second one is for the second signal, and the third one is for cross correlation result. So here I'll take subplot 3 1 1 and stem X. For clear view, let's fill this with magenta color. And now give the title of signal 1, and then plot Y in the same way. Stem Y and fill this with another color. Let's take red here. Now add the title of signal 2. So now we have our two signals x and y, and now to estimate cross correlation between them we have a built-in function named xcore. So we'll take a variable named rxy, which is equals to xcore and x and y, because we want to do the correlation of these two signals. And now plot this. Give the title of cross correlation xy, and run. So here we have our first and second signal, and in the end the cross correlated signal. Now have a look at the code for autocorrelation. First of all, take a signal. Let's say I'm taking x again, 1 2 3 4, and plot it. Here we only need two graphs, one for the signal, and as autocorrelation compares the signal with its own shifted version, so we don't need to plot that. And the other graph is for autocorrelated result of these two signals. So stem x, and again fill this with magenta for the clearer view. Now give the title to x as our signal. Now to estimate the autocorrelation, we'll use the same function that we have used for cross correlation, but here instead of using two different signals, we'll use both x, because that's what the definition of autocorrelation tells. So run this code, and you can see that we have our signal, and this one is its autocorrelated output signal. So these were the operations for the signals in the beginning level. Practice as much as you can.